Hi, welcome to Wien oscillators. This is also called as RC oscillators because we'll be using resistors and capacitors for the feedback configuration. This is a circuit diagram of the Wien oscillator where we have a op-amp for amplifier purpose, and we have resistors R1, RF. We decide the gain of the amplifier, and of course we have two RC networks connected in this fashion so that we can give the feedback. The type of feedback that we are having is positive feedback, so that's what is represented here. So this is the block diagram representation of Wien oscillator having the gain of A. There is a feedback factor beta given over here, and this A, since we know that we are not giving any input through the inverting input of the amplifier, whatever input that comes is a sampled version of the output voltage which is coming over here. So that's why it is a non-inverting amplifier. So the gain of this amplifier happens to be 1 plus RF by R1. So that's why the gain of this amplifier, which is there in the block diagram, is 1 plus RF by R1. And coming to the beta factor, the feedback pin. So we know that the input for this feedback network is coming from this, which is V0, which happens to be coming from here. And we know that the output voltage of this feedback network happens to be the input for this block diagram, which happens to be over here. So we are supposed to find what is VB with respect to V0, that is VB of S by V0 of S. Of course, I have written the final expression. Okay, before that, of course, as we discussed in one of the earlier video, this is what we have. If we just look at this one, so I have this series arm here, and then I have a shunt arm. The output voltage is taken across the shunt arm. So considering this series impedance as Zs and Zp, so I can write the output expression as Vin by Vin multiplied by Zp by Zs to Zp. So I can write the values of Zp as 1 over Yp, where Yp is the admittance of this parallel network. I'm just adding the admittance of resistance and the capacitance, which is this, comes out to be so and so. And Zs can be simply written as the summation of two impedances, which is this. So upon substituting all these values onto Zp and Zs, we will get this expression. We will get this expression. So upon simplifying, of course, you can certainly have this as expression. So this is what is the expression that I have written here. It is this is the beta expression, and we are looking at we know that for oscillations to occur, we need to have this CFS by RFS, which happens to be A by 1 minus A beta. For oscillations to occur, this has to become 1. So we are looking at what is A into beta. This is A into beta, where A happens to be 1 plus R by R1, that's what it is, and this is the value of beta. So this is actually the beta value. So you have A into beta given over here. Of course, this is the closed-loop transfer function. So you can write it this way. And finally, the closed-loop transfer function looks CFS by RFS as this particular equation. So let us try to understand as the value of A changes, how does this will behave? Because here, of course, it was said that suppose if A is equal to, we actually derived the condition for oscillation. So this can become, A beta can become 1 only when omega RC is equal to 1 over omega RC. So that you can write omega is equal to 1 over RC. So the frequency of oscillation is 1 over 2 pi RC. This can happen only when A is equal to 3. When A is equal to 3. So keeping this in mind, so let us try to understand the usage of this equation in both 20 sim to get the oscillations as a value of gain of the amplifier changes, how it happens. We know that this is the condition for oscillation. The value of gain is more than 3. Let us see what happens. If the value of A is less than 3, what happens? So we will just try to understand the variation of gain of the amplifier both in 20 sim as well as the actual circuit using LT-Spice. So let us first see uh, this circuit diagram using LT-Spice. Let us make the gain equal to 3. Let us see what is the oscillation that we are getting. Then let us make the gain greater than 10 less than 3 and try to understand, okay, how does the system will behave. So let me just try to open LT-Spice. I'm just trying to open here. Let me share the same thing. Okay, it's already there. Now if I open, okay, Wien oscillator is over here. Just open this. Okay, this is my Wien oscillator. Okay, we have already rigged up the circuit diagram. So only one condition that we are to satisfy here is that one of the capacitor should have an initial voltage of some value. So here I given the value of C as 0.1 microfarad and IC stands for the initial condition as 100 millivolt. So this is one required condition for getting oscillations. And we have set the gain of the amplifier as 3 here because now it is 2 and 1. The gain of the amplifier is 1 plus R3 by R4. Since it is R3 by R4 is 2K by 1K, which is 2 plus 1, which is now 3. So let me try to run this and then see what is the output. I have to get a sustained oscillation. Yeah, we are getting a sustained oscillation here. See now, this is the oscillation. We can actually find out the frequency of this. Frequency of this happens to be 1 over 2 pi RC, since the value of R and C is 1K and 0.1 microfarad. The frequency has to be 1.59 kilohertz. You can see it's almost there. So you are there at a frequency of 1.58 kilohertz. So this is with the gain as equal to 3. Let me just try to reduce the gain to maybe 1.9K. 1.9K will make my gain as 2.9. If I run it, now the poles will come on to left hand side. The system should have, you can see it is dying out soon. So it is dying out soon. So I can make this 1.99K. It just dies out very late. Now you can see this is now, the poles are just to the left of the H-plane. So this way we can see the oscillations are dying out since the gain is not equal to 3. Suppose if I make the gain slightly greater than 3, when I say greater than 3, RF should be more than 2K, definitely 2.01K. If I do this, you can see the amplitude is keep on increasing. So this is what is, so this is like a Odem system. The system is Odem system if the value of gain is more than 3. The system is underdamped if the gain is less than 3. The system is oscillatory if the gain is 3. This is 1.99K. System will be underdamped. See now it's an underdamped system. If you make the gain exactly equal to 3, because 2K will make the gain as 3. And see now it's a purely oscillator system. So a single system can be made to operate in 3 different conditions, that is stable, critically stable and unstable condition. Okay, this is fine. We could actually able to verify all the 3 possibilities of A equal to 3. Of course, we just made this equal to 3.01 and 2.99, so that it is slightly onto the left side and slightly onto the right hand side. So let us do the same exercise using what is that, 20 sim, and try to understand its working. So with my 20 sim, okay, let me edit the transfer function. Okay, since I'm looking at A is equal to 3, if A is equal to 3, okay, this is the equation. So it is 3e power minus 6 we already have, and then this is 9e power minus 3, 9e power minus 3, if it is okay, this is okay, leave a space and then give 1 there, and the denominator what I have, in the denominator I have 1 e power minus 6, so that is the coefficient of a square. Of course this is equal to 0 because you are treating a as equal to 3, and this is 1. So let me just do some things here. So quotient of a square is 1 e power minus 6, quotient of s is actually 0, that's why it is 0, and quotient of s power 0 is 1. If you apply and see the step response, okay, let me see the step response here. You can see you have the oscillations coming up. You can see this is an oscillatory system having a sine wave. We are exactly trying to simulate the Wien-Bridge oscillator, substituting this transfer function with a is equal to 3. You are getting a sustained oscillation, that is the time response. Let us try to make this a is equal to maybe 2.9. If I make it 2.9, then this will become okay. This will become 2.9 e power minus 9, and this will be 2.9 into 3 is 8.7. That is 8.7 into 10 power minus 3 is 0.087, and this is okay. Sorry, this would have been actually 3 in the earlier case. Let me make it 3 and then do it. Sorry for that. Let me just make this 3. This was 0.009, and this should be 3. What I try to do is, okay, this when you multiply this 3 with all this, okay, this is 3 e power minus 6, this is 9 e power minus 3, and this is 3. I'm just writing 3, and over here it is the same. Let me apply, say, step response, you get the same. Here, this is the response. So this is an oscillator response. Now if I make it as 2.9, we'll make it 2.9. This is 8.7, and this is also 2.9, and this will become, so as per this is 1 e power minus 6, whereas this will become 3 minus 2.9 is now 0.1 e power minus 6. It will be 0.1, sorry, this is e power minus 3. This is 3 minus 2.9 is 0.1 e power minus 3. E power minus 3, and then give a space and 1. Okay, if I apply now, this is the condition for a 2.9, which is less than 3. It should end up with a response which is underdamped, because see now this is the underdamped response. So if you can clearly see here, this is for a gain of 2.9. You can see we got the similar type of response in this LT spice also. So these two are one-to-one responses. You can see here. For this also you can see. Okay, let me just put all the 3 together somewhere here. Sorry. Okay, let me make this gain as 1.9k, which will make a gain of 2.9. If I run it, can you see this is coming down, which is 100% similar to that. So this is circuit, this is the transfer function, which is 100% highly clear. Of course, now let us try to make the gain like say greater than 3. So let me make this 3.1, that is a is equal to 3.1. When a is equal to 3.1, my transfer function becomes, what is my transfer function? My transfer function here it is, because this is a into 3 e power minus 6, it is now 3.1, and this will be 903.0093. 0.93 and this is 3.1. And here what happens to this now, it is 3 minus 3.1. So 3 minus 3.1 is 0.1 equal minus, it is actually minus of 0.1 e power minus 3. Apply now. See what is the step response. See now, step response is an Odem system. We are getting an Odem system if the gain of amplifier is more than 3. So that's what we saw here. See now, if the gain is more than 3, you have an Odem system, which we have seen there also. So of course you can observe one more thing. If the gain is more than 3, you can see the pole. Where are the poles? The poles are actually on the right hand side. If you see the poles here, can you see the poles have moved on to right hand side? You can see the poles are there here on the right hand side. That's why the system becomes unstable. The system is unstable because the gain is more than 3, which results in a pole to the right hand side. If you make the A is equal to 3 and this becomes 0, of course irrespective of this, whether it is okay, now this is what, 9. This will be now 3. Now this is the transfer function for gain of 3. If I apply this and then see this, can you see the poles are exactly on the imagined axis? They're exactly on the imagined axis. System is oscillated. System is oscillated. Suppose if I make this as 0.87, which is for a gain of 2.9. This is for, I think, 2.9 as a gain. Let me make this 2.9 on the numerator, and this becomes 0.1 e power minus 3. So I'm just substituting what is the value of A here. If A is 2.9, then this becomes 0.1 e power minus 3. And this is 2.9 to 2.9 to the power minus 6, and this is the quotient of this is 2.9 to the power minus 3, and this is 2.9. That's what I have. If I apply now, see now, the poles are there to the left hand side. See the poles are moved on to the left hand side. So this shows that system is now stable. System is now stable. So we can do similar type of analysis by applying some input also here. So what I do is, let me just demonstrate this as a system which is stable, critically stable and unstable. So for that what I do is, I will simply, because I know the frequency of oscillation is 1.59 kHz, let me use this as an amplifier now first. So what I do is, let me just delete this and take a source. I will take a source. Where is the source now? I think this is my source. I will take a sine source. I want to use it as an amplifier. Okay, let me connect this to. Suppose if you are having this as maybe 100 millivolt. Okay, this is 100 millivolt. Okay, just give me 1 minute. So let me just take it as a sine wave. This is sine wave with 100 millivolt as the amplitude. Let me take the frequency as 100 Hz. That's it. Now you can see the gain is 2.9 for this. For this it becomes minus 1.9. Am I correct? Because now this is the input that you applied. This becomes like an inverting amplifier. If I run now, see now, you have, okay, let me also see this input voltage. See now, is it acting like, even though initially you have this oscillations are dying out, can you see it is purely acting like an amplifier where it is a stable system? Because you know that all amplifiers are stable systems, meaning if you give a bounded input, now this is blue is a bounded input and this green color is a bounded output. Of course, we have a gain of whatever that is specified. What is the gain that we have? The gain that what I have now is 1.9. Because if you actually measure the peak to peak of this and peak to peak of output, it's 1.9. So let me see if the gain is equal to, suppose if you make RF as 2K, what happens? So what I do now, I'll make this now under this condition. This feedback network is of no use because it is not it's not satisfying that E beta is equal to 1. The moment I make this equal to 2K, the moment when I make this equal to 2K, even though you may think that this is still acting like an inverting amplifier with a gain of 2, but since because of this feedback network and this A beta is satisfying it as 1, see what happens if I run. See now, even though I'm applying an input voltage of 100 millivolt, you are getting these oscillations. Suppose if I slightly reduce the amplitude to 10 millivolt and run, see now, are you actually getting the amplification of this? So this output voltage is not the amplification of this 100 Hz signal. Instead you have the oscillations which is decided by this RC. Now suppose if you make this R is equal to maybe, let me make it as a 0.5K, and let me make this also as 0.5K or 500 ohm. Can you see now the frequency is going to double now? See now, this is, you are getting oscillations. Now the output voltage is not at 100 Hz. Output voltage is at a frequency decided by this RC. What I mean to say here is, now the same, suppose now you make the gain more than 3. So let me make the gain equal to maybe 2.1K as your gain. Now the gain becomes 3.1. If you see now, can you see it has saturated? Can you see it has gone to 12 volt? If you actually carefully see this, it has actually saturated. So if I just go back and see now from here, can you see this is building up and it has actually saturated here. So this is an Odem system. Now the system is unstable. Why the system is unstable? Because the poles are there onto the right hand side. So poles are there onto the right hand side now. So that's why it has increased and the amplitude cannot go beyond plus Vsat and minus Vsat. This is a saturated system. The gain is less than 3. It was not dying out in the previous case. So why it won't die out is because you have an input voltage. Suppose if the gain is 1.9K. What is the gain? The gain is less than 3, so that it doesn't act like an oscillator. Instead, it acts like an inverter. So it acts like an amplifier. The amplifier gain for this input voltage is minus 1.9. So if you run it now, can you see this oscillation will die out, but you have this amplification. Can you see whatever oscillation that was there initiated because of this will die out. Can you see this oscillation, this blue signal is being get amplified by whatever the gain that is intended. Can you see this oscillation is dying out, whereas you have the amplification action happening. Meaning to say, yes, the same amplifier, if the gain is less than 3, it acts like an amplifier. This circuit with an input voltage here, if the gain is less than 3, it acts like an amplifier. The gain is equal to 3 irrespective of this input voltage. It will give the oscillations as per the RC value. If the gain is more than 3, it will start the oscillation and then the oscillations will saturate. So this way, able to verify the theoretical concept of Wien bridge oscillator, both using circuits as well as using the 20 sim. So 20 sim we saw where were the poles located when the value of gain is 3. When it is less than 3 poles are there on left hand side. If the value of gain is more than 3, they were there on the right hand side of the display. So this is a very good example of operating oscillator, operating a circuit with different values of gain. System will be stable, oscillatory as well as unstable.